So far we have discussed about the lattice, its types, the different types of unit cells, and the number of atoms in unit cells. So today's class is based upon the packing of atoms, or packing in solids, we better say it. Now, packing in solids is based upon the assumption that atoms or the molecules or the ions, they are spherical in shape and they are rigid. Means we say the atoms are spheres and the spheres are rigid. On this assumption, the entire packing is based. Now, first we take the packing in two dimensions. Now, in two dimensions, we have two options for spheres to get packed to form the lattice. In the first case, we see this is the first layer or first row of the atoms. The second row of the atoms is just below the atoms of the first row. The third row is just below the atoms of the second row. So we can say there is horizontal as well as vertical alignment of the spheres or the atoms. Now, if we choose any sphere, suppose we have the sphere marked with this cross. This sphere is in touch with four different spheres. Like this particular sphere is in touch with this sphere, is in touch with this sphere, this sphere, this sphere, and this sphere. Means the four spheres are touching this given sphere. If you join the center of these four spheres, it takes the shape of a square. We call this type of packing as square close packing. And the space which is left between these spheres or the atoms is known as void. It may be known as interstitial space or interstitial void. Now, this is the first possibility that atoms they pack accordingly. The second is the first row of the atoms. The second row of the atoms is in the depressions of the first row. Depressions means if this is the first row, these are the depressions in the first row. So the atoms of the second row, they are in the depressions. They are not just below the atoms of the first, like in the case of sphere. They are just below one another. But here the atoms of the successive rows are in the depressions like this. If this is the depression, the atom of the successive row is in the depression. So this is how the atoms they arrange themselves and form a pattern. Now in this case again we choose a sphere. Again I choose this sphere marked with this cross. This particular sphere is in touch with 1. You can see here 1, 2, 3, 4, 5 and 6. These 6 spheres are touching this given square. Now if I join the center of these 6 spheres, it takes the shape of a hexagon. This type of packing is called hexagonal close packing. Now, the number of spheres which are touching a particular atom or a sphere, they are known as nearest neighbors. So, number of nearest neighboring atoms in a lattice is known as the coordination number of a given sphere. Means we can say in square close packing, the nearest neighbors are 4. The coordination number of this sphere is 4. You can choose any sphere in square close packing. Its coordination number comes out to be 4. Now here the nearest neighbors are 6. It means the coordination number of hexagonal close packing is equal to 6. Now you can very well see that the size of the voids in square close packing is much more than that of hexagonal close packing, or we can say this hexagonal close packing is more efficient than square close packing. This is more tightly packed packing than square close packing. So when the solids they go for three-dimensional packing, they reject this square close packing in two dimensions itself, and they likely to form layers on hexagonal close packing. Layers means this is the first layer, this is the first two-dimensional layer, the second layer, the third layer, the fourth layer, to give it a three-dimensional structure. So the solids have to choose between square close and the hexagonal close packing. And since hexagonal close packing is more efficient, more close, the three-dimensional packing take this as a base layer to form the three-dimensional structures. Now we take packing in three dimensions. In three dimensions, three-dimensional packing in solids. Now in three-dimensional packing, we take hexagonal closed packing as the base layer. Now we place the second layer of atoms over this layer. We are going to place a second layer of atoms on this base layer. Now see, now in this hexagonal closed packing, if I again draw the structure, see we have two type of triangular voids like this. So this type of void, these are the triangular voids formed in the hexagonal closed packing. Now we classify these two voids as the triangle upward with apex upward. This is the triangular void, like this is one void, this is another void. So we call this type of void as A type of void, and with apex downward we call them as B type of voids. See, you can very well see both all are triangular, one with apex upward, another with apex downward. So we classify them as A voids and B voids. So I am coloring A voids here as red. Now the second layer of atoms is placed in such a way that they cover A type of voids completely. Like if this is the A void, the second layer atom is placed over this A type of void. So all the A type of voids, they get covered completely by the atoms of second layer. So you can see this type of structure will appear. Now these figures are very well explained in the PDF. You go through the PDF so that there will be more clarity of these figures. I'm just trying to explain that how we are placing the different layers. So this is layer A. We mentioned the first layer as layer A. The spheres drawn with the blue pen, they are layer A. Now these red spheres, they are the second layer spheres, and they are present on the A voids. See, like this. So all the A voids are completely covered by the atoms of the B layer. Now you can see this B type, small B type voids, they are partially covered. You can see this is one A atom, B layer atom, second B layer atom, and third B layer atom. So they are covering A void completely, but this B void, which I am showing you with the green color, this is partially covered. This is partially covered. Like I have tried and explained it here. 1, 2, 3. These are the atoms of A layer. These are red are the atoms of the B layer, and this is the partially covered B void. This is partially covered B void. So now we have two layers, layer A and layer B. Now the third layer is again placed in such a way that atoms of the third layer, they are just above the atoms of the A layer. Means now we are repeating A layer again. The third layer is same as that of A layer. The fourth layer is same as that of B layer. Means we can say here we have AB type of pattern which is to be followed. A layer, B layer, followed by A, again B. AB type of packing in 3 dimensions is known as hexagonal close packing. This is the actual hexagonal close packing. Now if the third layer, अब यहाँ पर the third layer is same as that of the first layer, so we have given the name A again. The fourth layer is same as the B layer. We say second layer we given the name B, so we have the pattern AB. Now if we have another option like we have layer A, layer B. Layer B is what? The atoms of the layer B, they are completely covering the A voids. Now the third layer is placed in such a way that it covers the partially covered void. अब यहाँ B layer में, in this B layer we have partially covered small b type of voids. So the third layer is shown with this green pen. The atoms of the third layer, they are placed over this partially covered void in the second layer. We have first layer, second layer is covering A type of voids. The third layer is now covering B type of voids, small b type of voids which remain partially covered in the second layer. So we have this type of structure. A layer, red one is B layer, third one is known as C layer because this third layer is different from A and B. Now the fourth layer is again placed over the atoms of the A layer, means we are going to repeat the pattern ABC, ABC. So this ABC, ABC type of packing in 3 dimensions. We have 3 different layers. The pattern is ABC, ABC, and this ABC, ABC type of packing is known as cubic close packing. So now in this layer, in hexagonal close packing and in cubic close packing, the more efficient packing is cubic close, because here you cannot see any void which left uncovered. All the void gets completely covered. So cubic close packing is more perfect than hexagonal close packing. Now see, when we have the hexagonal close packing, here we have triangular voids which get covered with the atoms of the B layer. Now see, there we have the formation of two type of voids in hexagonal close packing. One is tetrahedral void, another is octahedral void. Now what is tetrahedral void and what is octahedral void? Now see students, these three are the atoms of the layer A. 1, 2, 3, and they form a triangular void with apex upward, that is small a void. This is small a void. Now we have placed the atom of the second layer over this to completely cover this a void. Now we have four atoms which completely covers this triangular void. Three atoms of the base layer, one atom of the second layer. Now if I join the center of these four, see, these were the three atoms of the first layer and we have placed one atom over here. Now if I join the center of these four spheres, I try to join the center of these four spheres, so three spheres and one is above it. Three spheres and one is above it. So these four, when we join the center of these four spheres, it takes the shape of a tetrahedron. You can see the shape is tetrahedral. So this void is known as a tetrahedral void. Now if we place anything in this void, this comes in contact with these four spheres, means the thing which is placed, an atom or the ion which is placed in this void, it is in touch with these four spheres. So we say the coordination number of the tetrahedral void is 4. Now if we see this partially covered void, this is partially covered B void. 1, 2, 3 atoms of the first layer, 1, 2, 3 atoms of the second layer. So this partially covered void is in touch with 6 spheres. 3 from the layer A, 3 from the layer B. Now if I join the center of these 6 spheres, it takes the shape of an octahedron. I cannot show you the structure here, it is well shown in the PDF. So upon joining the center of these 6 spheres, it takes the shape of an octahedron. The void is known as octahedral void. So you may have to define a tetrahedral void or an octahedral void. So just write down the definition. A tetrahedral void is the void which is formed by the combination of four spheres. Upon joining the center of those, it takes the shape of a tetrahedron. The void thus formed is known as a tetrahedral void. The coordination number of tetrahedral void is 4. Now octahedral void. The void formed by the combination of 6 spheres. Upon joining the center of those 6 spheres, it takes the shape of an octahedron. The void formed is called octahedral void. The void formed by the combination of 6 spheres, and if we join the center of those 6 spheres, it takes the shape of an octahedron. The void is octahedral void, whose coordination number is 6, means anything placed in this void is in touch with 6 spheres. So we say the number of nearest neighbors are 6. The coordination number is 6. Now it is observed, it is seen that number of tetrahedral voids are double the number of spheres. The number of tetrahedral void is double the number of spheres, while the number of octahedral voids is same as the number of spheres. Now I will try and explain this. Now see, we have 3 layers, 3 atoms of the first layer, and the second one atom which is covering this void is of second layer. Now the third layer, that is again, the third layer is just above the atoms of the A. So I have this hand, 1, 2, 3 and one single atom, again 1, 2, 3. So this single atom is forming a tetrahedral void with the layer below this and one with the layer above this. This single is The tetrahedral void, the 3 spheres of layer A and 1 sphere of layer B. Now the third layer is placed just over the spheres of layer A. In 3 के ऊपर वापिस 3. So this single atom is forming a tetrahedral void with the layer below and a tetrahedral void with the layer above. It is covering one triangular void of the lower layer and one triangular void of the upper layer. You can always imagine this is a 3-dimensional structure. You have to visualize. So 1, 2 layers, and you have one sphere of the B layer. It is sandwiched between the two A layers. So this B layered atom is forming two tetrahedral voids. This single atom is forming two tetrahedral voids, one with lower layer, one with upper layer. So we say the number of tetrahedral void is double the number of sphere. One sphere is forming two voids, right? But this cannot be seen in the octahedral void. It is formed by the combination of 6 here. Not single atom is responsible for the formation of two voids. So here the number of spheres is taken as same as the number of octahedral voids. Octahedral voids are same as the number of spheres. Now this you must underline. On this concept we have a large number of problems that can come for 1 marks. Now for example, I have one question written here. A atoms forms the lattice and B atoms are present in all the tetrahedral voids. So A is forming the lattice and the voids which are there, they are filled by the B atoms. So let us say the number of A atoms be n or 100 or x, whatever you want to take. The number of tetrahedral voids are double the number of spheres. So if the spheres are n or 100, the tetrahedral voids are 200 or 2n. And the number of octahedral voids is same as the number of spheres. So octahedral voids are 100 or n. So whenever you do this type of problem, first thing you write these three things: number of atoms, tetrahedral voids, and octahedral voids. Now according to this question, if A forms the lattice, let us say the number of A be 100 and B is present in all the tetrahedral voids. So B, the number of tetrahedral voids here are 200. They are present in tetrahedral voids. So the number of B atoms in this lattice is 200. So A is 100, B is 200. So if you simplify this, the formula comes out to be AB2. This is how we get the formula based upon this concept. Now, another question. If A forms the lattice and B atoms are present in 1/3 of the octahedral voids, write the formula of the compound. Let A be 100. The B is in octahedral void. So octahedral void, the number is same as the spheres. It means the octahedral voids are also 100. Now out of this 100, only 1/3 is occupied by the B atoms, 1/3 of the octahedral voids. Right? So A is 100, B is 100 upon 3. The formula will be A3B. So I'll give you a number of problems like this at the end of this class. You do that. Any doubts, you can always ask. So this is about the packing, the different type of voids. Now one thing more, like when we say the cubic closed packing, in cubic closed packing, the third type of void is the cubic void. The cubic void means again the center of the room, the within the cube, the space which is within the cube. Again, I take the example of the room. The space within the walls between the roof and the floor is taken as the cubic void. And the coordination number of cubic void is 8. Because we have 8 corners, so the coordination number of the cubic void is 8. Coordination number of tetrahedral void 4, octahedral void 6, and cubic void is 8. Now next thing is we need to talk about the packing efficiency. What is the meaning of packing efficiency, students? Packing efficiency means how efficient, how tightly packed is your lattice. So for that, we calculate the percentage packing efficiency. Percentage packing efficiency means out of the total volume, what volume is occupied by the spheres, that is by the atoms or the molecules, and rest is your voids, rest is the empty space. So packing efficiency is defined as the number of atoms, it is the volume occupied by the spheres in a unit cell is the packing efficiency. The total volume occupied by the spheres in a unit cell is packing efficiency. Now when we get the percentage packing efficiency, we use the formula number of atoms per unit cell into volume of each atom, the spheres present in a unit cell, upon volume of unit cell into 100, because this is percentage packing efficiency. Now let us again assume the edge length of the unit cell be A picometers and the radius of the sphere is R picometers. Edge of the unit length A, unit cell A, and the radius is P. Again I am telling you once again, the unit cell which we are discussing here in class 12, it is a cubic unit cell where A is equal to B is equal to C, alpha is equal to beta is equal to 1. Now we first take the packing efficiency in simple cubic cell. In simple cubic cell. So in simple cubic cell, number of atoms per unit cell is equal to 1. Z is equal to 1. Now see, this is the structure of the simple cubic cell. One atom is present at each corner of the cube. So see, whenever we talk about the packing, these spheres, they are touching one another. It is very difficult to show them in 2 dimensions. But actually these atoms, they are so tightly packed, they touch one another. Like here I tried to show. One atom is present at each corner of the cube. So this edge length, this is called the edge length of the cube, right? And this be the radius of the sphere R, radius of the sphere R. So it means in simple cubic cell, the edge length A is equal to 2R. This is clear from the figure that edge length A can be taken as 2R. Now, since the unit cell is a cube, the volume of the cube is again equal to the length cube. The length here is A picometers, so we write it as A cube. Now, the number of atoms in simple cubic cell, Z is equal to 1. So, number of atom is 1. The volume of the sphere is given by 4 by 3 pi r cube. So, 1 into 4 by 3 pi r cube upon A cube into 100 will be percentage packing efficiency of simple cubic cell. Now, 1 into 4 by 3 pi r cube, since we have the relation between A and R. So, to solve this, to simplify this, we substitute A by R. So, A can be substituted by 2R. Instead of A cube, we are writing 2R cube. Now, when we solve this, we get 52.4%. It means the packing efficiency in simple cubic cell is 52.4%. What does it mean? That out of total volume of the unit cell, only 52% is occupied by the sphere. This rest is a void. So this is how we will calculate the packing efficiency in face-centered as well as in body-centered cubic cells. FCC, face-centered cubic cells. Now in face-centered cubic cell, the Z is equal to 4. That is the number of atoms per unit cell. We have calculated this in the last class. Z is equal to 4. Now see, I am taking here only one face of the cube to simplify the things. What is face-centered cubic cell? One atom at each corner and one in the center of each face. So here I have taken only one face. So one atom at each corner, one at the center of each face. These spheres are also touching, but here I cannot show. If I try and touch them, it becomes very cumbersome. So you see, one atom at each corner, one in the center. Now, if I join the center of these spheres, the one which is present in the center and at the corner atom, if you join the center of these spheres, this becomes AC. Now, every triangle in a cube is always a right angle triangle. Any triangle formed in a cube is a right angle. You can always imagine you are sitting in a room, you can always see walls पे triangle बनाने की कोशिश करो, diagonal triangle बनाने की कोशिश करो, तो it is always a right angle triangle as the walls are all perpendicular to one another. Now in this, so if it is a right angle triangle, ABC is a right angle triangle, we'll follow the Pythagoras theorem, according to which the diagonal AC square is equal to AB square plus BC square. Now AB is the edge length which is taken as A picometer. BC is the edge length again taken as A picometer. So A square plus A square is equal to AC square, which is the diagonal of the triangle. Now AC square is equal to 2A square, or AC is under root 2A. It is simple maths. Now this AC is equal to, these are the different spheres. This be the radius r, twice the radius 2r, r means AC can be taken as 4r. So substitute this AC as 4r. 4r is equal to root 2a. So A is 2 root 2r. If you simplify the things, you have the relation between A and r. This may be asked in your exam for 1 mark. What is the relationship between the edge length and the radius of the sphere in face-centered cubic cell, in body-centered cubic cell, or in simple cubic cell? So in simple cubic cell, the relationship is A is equal to 2r. In face-centered cube, the relation between the edge length A and radius is A is 2 root 2r. Now apply the percentage packing efficiency formula. Number of atoms, which in this case is 4. Volume of each atom, being sphere, it is 4 by 3 pi r cube upon volume of the cube A cube. So again here this A gets substituted by 2 root 2 to do this calculation. So A substitute kar diya and you will get 74% as the percentage packing efficiency of FCC. The percentage packing efficiency of body-centered cubic cells. Now here, the number of atoms per unit cell comes out to be 2. Z is equal to 2 here. Now, see, body-centered means one atom is present in the center of the body. So you again imagine the room as a cube. One atom is present in the center. Corner atoms will, you draw a line which pass through the corner atom, through the body-centered atom to another corner. So if I tried and explain here. So see, this is the atom. This is the atom which is present in the center of the cube. And this is present on one corner of the room. This is present on another corner of the room. When you need to draw, अपने देखो उसमें ध्यान से. This is one face. इस पे corner पे I draw one atom. This is the back face, जिसके corner पे I draw another atom. ये back face पे है. This is front face and this is in the center. तो you imagine in the room, center में एक atom रखा हुआ है. एक room का corner उधर ले लो, उसके opposite एक corner नीचे. So if you visualize, you can have this structure. Now see, if I join the center of these spheres, that is corner and the body center, you have this line which is A and B. A and B. I'll try and make it again. See if this is a room or a cube. This is the one which is present in the center of the cube. This is one atom. ये front वाला face है. This is the front face. इसके corner पे हमने लगा दिया एक atom. And this is the back face. ये पीछे वाला face है. इसके corner पे हमने लगा दिया. If we join the center, we get this line. Now this is A and this is B. Now see, we cannot find AB because we do not have this value. ये complete one is A, but we do not have this value. So to get the value of this AB, to find the relation between A and R, again we'll first draw a diagonal on this face of the cube. And we mentioned it as C. C. And let this be D. Now when we draw a diagonal on this floor, now this becomes a right angle triangle ABC. ABC becomes the right angle triangle. Now this is the diagonal. Again diagonal AB. Sorry. We first take this triangle BCD. We take BCD. In BCD, BD square plus DC square is equal to BC square. This is the diagonal of this face. BC square is BD square plus DC square. Now this is again edge length A. This is again edge length A. So A square plus A square is equal to BC square and this BC square is equal to 2A square. Now we take the triangle from here. So we get this BC. Now we have this bigger triangle now ABC. AB square is the diagonal now. AB square is equal to BC square plus AC square. This is again edge length A. This we have already found from this lower triangle. So substitute this. You have AB square as BC square. AB square as BC square plus AC square. This is your BC square and this is AC square. So AC is AB square is equal to AC square plus BC square. Now AC is equal to again edge length of the cube, A square, plus BC we find out 2A square. So this is 3A square. Now AB is equal to under root 3A. Now what is AB? This is again 4R is equal to root 3A, or A is equal to 4 upon under root 3. This is what we did here. So A is 4 upon root 3R, right? Or R is equal to root 3 upon 4. This is the relationship in BCC. Now to get the percentage packing efficiency, again use the formula. Number of atom here is 2. Volume of each sphere 4 by 3 pi r cube. Volume of the cube is A cube. A is substituted by 4 upon under root 3 R. 4 by under root 3 R cube into 100. To be 68%. So this is the packing efficiency in BCC. So we for face centered 74, BCC as 64. So you can very well see that which packing is the most efficient packing. Which type of unit cell will give you the most, that face centered cubic cell. You see the packing is most close packing. So this is about the packing efficiency in solids, and this is for today's class. So I'll write down certain numericals for you to do them. Now you make the notes with the help of this class as well as through the PDF. Maintain your separate register, write down everything. Any doubts you do write, and you can ask me through WhatsApp, or if I take the live class, if you people not do mischievous things, behave properly, I will take a live class to take your doubts. So do all the things in your notebook and keep a record. Thank you.